We're going to be talking about wireless networks today. Just kind of introduce the concept of it, and then we'll get into specific protocols in next couple of lectures. Before I did that, I wanted to talk about port forwarding. I was supposed to talk about that last lecture, but we ran out of time. Kind of in the same vein as last lecture of it being more a practical thing. This is this kind of practical discussion of how to set up port forwarding and what does that even mean when someone says port forwarding. We have enough information now to know what that looks like and how to set it up. It can be a useful thing to either know if you want to do it or not want to do it. So the problem is, we talked about servers and, they want to be available publicly, accessible from anywhere, a well-known IP address or well-known host name, something that doesn't change. But not everyone has that, right? You can pay money for that. That's not hard to do that, but sometimes you don't want to do that without having to set up all the infrastructure. So what if you want to have a server running in your house? Okay, so what does that mean? If you have a server running in your house, that actually means has two implications. First one shown here is that you're behind a NAT. Typically, not always, but 99% of the time you're behind a NAT. Worst case, you might be behind two NATs, and then that's a really big problem. Then you can't set port forwarding. But for this case, let's assume you're behind one NAT. Okay, you're behind a NAT, so that's one implication. Is now when a client, if I draw here, client wants to send you, that was a little too aggressive. Anyways, it won't be able to send you a request. It'll get blocked at the NAT. The NAT will see an incoming packet. It won't necessarily be blocked, but the NAT will see this incoming packet and look at its table and say, oh, I don't know what this mapping is, and then it'll just drop the packet. So that's your first problem. So let's talk about how we deal with that problem. We use port forwarding. We essentially put a hole in our NAT. Let's draw a little hole right here, or a tunnel you might want to call it, into our NAT. Say, hey, allow a certain port. You can choose whatever port you want. Let's port, 8,000. Oh man, 8,000. So I'm going to choose port 8,000. I'm going to open that up. Say, hey, if something comes in on port 8,000, then do something. Don't just look in your NAT table and drop it if there's nothing there. Go to a different table, and that table has a mapping of an IP address, an IP mapped to also, and a port number. A port. You say, when you get a packet on that incoming port number, port 8,000 in this case, send it to a different computer. Because you're not going to send it to itself, the router. You don't ever really send data as the router as the last destination. You send it to a server or to another client. In this case, it's a server. So you tell it this mapping. And so let's say we want to send it to this server on a certain port. Maybe it's port 80. That's a cool thing. You can map from 8,000 to 80. Or let's say you want to set up an SSH connection. Maybe then it's port 22. So your server doesn't know it's behind a NAT. Just, I saw a connection on port 22. But your NAT knows that actually, and clients have to go to port 8,000, but your server doesn't know that they went to 8,000. They think they went to 22 or 80 or whatever, some common port. So that's what port forwarding is. You need three pieces of information. You need what is the external port at which a person would go to and which you're forwarding it to internal IP address and port number. So that's port forwarding real quick. But remember I said there's two problems. So that was the first problem, was the NAT. But the second problem that is, well, how do I know what's the host name of this server? Of course, it's got an internal IP address, so we don't know its IP address. So maybe the better question is, what's the external IP address of your router? The router's got, you can kind of think of it right like this. It's got the internal part, and then it's got the external part. So what is the external? Put a question mark there. How do we figure that out? If you're running a real server, not behind a NAT, not behind a router, you would just, pay someone DNS, pay a DNS provider and say, hey, here's my static IP address, map this to a host name. But the problem is homes don't have static IP addresses, not usually. You can pay money to your ISP to get static IP address. Uh, and maybe it's semi-static in that like it might change once a year, but still you don't want your whole all your services to break down if it changes once in that year. So I've also had ISPs that it's changed once a month, or anytime they want. So having that your IP address, your external IP address changing is not a good thing. That's one of the features of a NAT is that can change and it has no impact on your internal network. So that's a cool benefit of a NAT. But when you want to do port forwarding and you want to set up a server in your home, then having a dynamic external IP address is a problem. So how do we solve that problem? What we can use is a service called Dynamic DNS. And so what this does, Dynamic DNS, is we add an extra level of redirection, I guess, similar to what DNS does, is where we talk to a third-party service, some kind of dynamic DNS called DDNS, and we update our mapping to a given host name. So let's say my server, also its job is to occasionally reach out to this dynamic DNS provider and say, hey, this is my external IP address. In fact, it doesn't even actually have to really do anything. It just has to actually send a simple request, and the dynamic DNS service will just look at that packet and say, oh, well, I know where you came from because I have your external IP address because that's in the IP packet. So really there actually is very little that the server has to do, just besides sending a request, doing it on an hourly basis, on a minutely basis, whatever you think. I don't know what the actual default configuration for these things are. And so what this dynamic DNS service does is it will keep on updating your mapping between a domain name and your external IP address. So if the external IP address ever changes, within a minute or hour, your dynamic DNS service will know that and it will update. So now the client actually won't go directly to your server. It'll first ask the dynamic DNS service. It doesn't know it's asking. It just, you have it set up. It'll just ask DNS, and DNS will talk to the dynamic DNS service, and they'll say, okay, here is the external IP address of the thing you're trying to talk to. And then from there, you'll go to the device. A popular dynamic DNS service is DuckDNS. It's free, that's why it's popular. It's pretty lightweight. It's got lots of support. Sometimes, I said the server does the pinging. Sometimes you can actually have it built into your router itself, can support dynamic DNS. That's not an uncommon feature of nice-ish routers to have that actually built in. So you don't even have to have a server running. Some people do this with Raspberry Pis. I think Pi-hole has this capability. So it doesn't have to be a very intense device in order to do this. But those are the two problems. So first you got to traverse the NAT, and then how do you know where the NAT is? You use dynamic DNS. This is kind of a hard concept to explain to people that don't know much about networking, but now that you guys know a lot about networking, it should all make sense, kind of all these problems that we're seeing and how we get around these problems. Okay, so that's it for port forwarding. Now let's get into the wireless stuff. Okay, let's do laser pointer. Okay. So I'm going to give a little introduction about wireless protocols, wireless infrastructure, wireless networking. That's the word I'm looking for, in general, and then we'll cover some of its characteristics in this lecture. I think this will be a relatively short lecture, and then next on Friday we'll talk about Wi-Fi, and then on Monday we'll talk about cellular networks and IoT. We'll maybe briefly mention mobility. We won't go as deep as what this says, though, but it is interesting mobility. Okay, so here, you've seen this picture kind of before, but there's more diversity in it. Now it's just got only wireless links on the edge. So I do want to be clear about that. There's sometimes confusion among people of where is the wireless. The wireless is really only on the edge of the network, the first hop, as we call it, right? everything else is pretty much wired because that's you want that all to be really reliable. And so rarely do you find wireless links. I guess I would say never. I've never heard of it, but I guess it could be done. You find wireless links in the actual infrastructure that's all done wired because you want that to be done really reliably and has to travel far distances and stuff like that. So let's see. We have our end host, just like normal, network, wired or otherwise. Uh, they run applications. We have maybe a little bit more diversity of nodes in that we can have a little IoT sensor, we can have a smartphone, whereas wired you had to be plugged in, and so that's a little more cumbersome. But now we're also able to have mobile nodes. They don't have to be mobile; they could be stationary. There's still benefit to not for it to be wireless even if it's stationary. But now we have the ability to be mobile easier. And so we're all familiar with this now. Laptops, right? Smartphones. They wouldn't really be possible if they weren't, if we had to, plug in to get to the internet. Okay. How is this wireless information relayed? It's through a base station. That's the general term for kind of the central point of coordination that converts from a wireless link to a wired link. Every protocol has their own terminology for this. Base stations kind of just the more general term. Wi-Fi, they call them access points. Cellular, they call them cell towers or E node Bs or G node Bs. Got lots of terminology. LoRa, the LoRa wireless protocol, long range wireless protocol called LoRa is called some gateways. Uh, so everyone has a different terminology, of course, but at the end of the day, there's base stations. They convert the wireless signal to a wired and then pass it up the infrastructure. And then, of course, we have the wireless link, the glue that holds those two things together, the end host and the base station. There's lots of different wireless protocols. If you're interested in this, you could take my wireless communications class, wireless networking class. 526, I'm going to be teaching it not this winter, but next winter. A lot of interesting stuff happens here. We got, different wireless protocols, multiple access control protocols that play a very big role of how to coordinate between these wireless nodes. Certain frequency bands lend themselves better for better distances, better data rates. So there's a lot more to play with in this space than there is with wired, in my opinion. So yeah, but the wireless link has a big influence on what type of mobility you can see, what kind of data rates you can have. To that point, here's a nice chart I like to show, showing on the x-axis the different kind of categories of ranges of wireless protocols, going from indoor all the way out to like a long range, kilometer distance. And then on the y-axis, we have speeds. How fast can we send the data? 2 megabits per second, all the way up to 14 gigabits per second. That's pretty optimistic. So yeah, kind of what trade-offs do you want to make? You can see these 802.11s. That's all Wi-Fi. Maybe I should have said that first. 802.11 is the standard name, like the IEEE name that the standard is given. Wi-Fi is actually just a marketing term. It's actually 802.11, and then we have these letters BG for the different generations of Wi-Fi. Now it's Wi-Fi 4, 5, 6, 7. They've actually rebranded that to make it a little bit more clear to consumers. But anyways, you see that a lot of the Wi-Fi has lived in the indoor domain, as what you expect, right? Wi-Fi is not typically widely deployed in outdoor settings. It can be, but it doesn't work super well, and it's just not really meant for that or used often for that. Though the newer versions of it have started kind of playing and going outdoors more, with one exception of 802.11 AF and AH. This is kind of a weird tangent. Actually, kind of even though it's part of the spec, it uses a whole different frequency range and a different modulation scheme. So to me, it's more like a cousin of Wi-Fi, and then it targeted much more like outdoor, long range applications. Wi-Fi, as it's gone better, has gone just faster data rates. We have down here Bluetooth. We know that is not designed to be outdoor at all, and it's not designed to be really high data rate. You might say, well, what's the point of Bluetooth? I think hopefully you probably know what the point of Bluetooth is it's really low energy. So there's a third axis here that we haven't really shown is energy usage. And as you might expect, there's a trade-off here. The farther distance or higher data rate, the more energy it uses typically. We have yet to find the silver bullet of something that uses low power, high data rate, and long range. Honestly, I think that's probably a paradox. You probably can't actually do that, but that'd be awesome if someone could find that. And then we've got cellular, 4G and 5G, mostly targeting outdoor long range distances, just with the data rates getting faster. Here's another way to think of this in terms of on the x-axis here. Now we have what kind of area are we trying to cover? We've got wide area, so that's WAN, we call it wide area network. Long distances. Then we've got neighborhood area networks, building area, home area. Home area is more like your LAN. These are what we would call a LAN typically. And then you got body area, BAN. There's even like other different LANs and WANs and all this sorts of stuff. So body area, you got things like Bluetooth and Zigbee, and these other protocols are really designed for low data rates. On the y-axis we have data rates and bits per second all the way up to gigabits per second. So there are some things, really body area that uses terahertz, really high frequency, like 60 gigahertz or terahertz communication. But you have to have line of sight. They have to be really close to each other. Otherwise they don't work. So yeah, it's only meant for a body or like, a couple of feet, but you can get really fast data rates. Got our different Wi-Fi's right here, all kind of living with the same area, supposed to be working in a building. It's gone better and faster. We see some exceptions of Wi-Fi mesh where it's able to travel further between neighborhoods. This is Zigbee right here. And there's other wireless protocols that are designed for more home or neighborhood area networks. And then we got our cellular networks over here. There's this interesting line right here of all these protocols on this side live in unlicensed spectrum. What I mean by that is you don't need a license to use it, to operate equipment. Call them ISM bands because they're meant for instrumentations and scientific measurements. So these are frequencies that no one really wanted, and so they said, oh, science can use it, sure. And it's kind of crazy that Wi-Fi in this not so great spectrum, specifically 2.4, there's also 5 gigahertz and 900 megahertz, has been able to make a really good protocol in not that great of spectrum. I would ask you guys, why is 2.4 gigahertz a bad piece of spectrum? And one of the reasons why it's a bad piece of spectrum is because it's the resonant frequency of water. So that's actually the same transmission that your microwave uses to excite the water molecules of your food, right, is 2.4 gigahertz. So it doesn't work very well on water, Wi-Fi, because water absorbs it so well. So that's one reason why they said, we don't need 2.4 gigahertz. It can be unlicensed. But pretty much all the good spectrum is licensed, meaning I have to pay millions or billions of dollars to own that frequency, or at the very least, I have to get a license to use it. So that's like ham radio as an example of where you have to get a license. Example where you have to pay millions or billions of dollars is like AT&T or T-Mobile. They own certain frequencies, and they're the only ones that are allowed to use it, or their handset. So if I want to transmit on that, I'd be breaking the law. And so they own that frequency. Just as a quick tangent, that's the paradigm we've been using up to this point in the United States is, I call it frequency or spectrum auctions, where they actually auction off the spectrum. They say, hey, 1.3 gigahertz is open, for this frequency range. Who wants to buy it? And then big companies bid on it, and they get it, for millions and billions of dollars. That's worked so well so far, but we're actually starting to reach a point where it's overcrowded. We've run out of really good usable spectrum, and so we're transitioning in the next 10-ish years, I think, away from that model to a different type of model. So it's really exciting from a spectrum standpoint, spectrum coordination, what we're going to do to deal with these issues. Don't get me started on this. I think it's a really interesting topic. I'd love to talk to you more about it, but let's keep going. Okay. There's two different typical modes of a wireless network. There's what's called infrastructure mode. That's where you, another word would be a hub and spoke, where you have these nodes all in a circle around. They don't actually have to be in a circle, but they're connected in a circle around to a hub right here. So a gateway is a sub kind, and then that gateway takes care of the translation and the communication. So it's really only one hop then. So that's infrastructure mode, base station connecting to mobiles. What's interesting in infrastructure mode is the concept of handoff. What if I'm transitioning from one base station to another? So this case, maybe from one cell tower to another. How do I deal with that? That can actually be quite challenging. And cell networks are really good at handling that. You can be on a phone call, right, and driving your car and pass off between different cell towers and not even notice, and your call doesn't get dropped. That's not by accident. That took a lot of work, a lot of engineering went into that, making that possible. And uh, Wi-Fi or cellular is super complicated as a result of that, in part as a result of that. Wi-Fi, on the other hand, I know these are little cell towers in my opinion, but Wi-Fi does not handle that as well. It's gotten better and there's been improvements to Wi-Fi, but that's not one of Wi-Fi's basic primitives, is walking down the hall and switching between access points seamlessly. I think it works pretty well, but I don't think it's quite as seamless as cellular. Not as much work has been done on it to handle it as well as cellular. The alternative to infrastructure mode is ad hoc mode. This is where you have no base station. Just each node acts as a base station, so it both can transmit data and receive data, or route data, I should say. Because of course, back in infrastructure, I can send and receive, right? Send to the base station. When the base station has information, it sends it to me. So that's bidirectional. Same thing here, but now these center nodes might act as relays. So maybe I'm node A and I wanted to send to node Z over here. These node A, B, and C will act as, or B and C will act as relays to send the data. Really powerful idea. Honestly, hasn't panned out very well. We tend to stick with infrastructure mode. Pretty much all big deployments are this infrastructural mode. Ad hoc networks have some really cool implications. You don't need infrastructure. Great for military applications, right, where you don't want one central point of failure. But it's also a really hard problem because you have to constantly organize yourself and figure out how to get data from one place to another. And what if maybe a key node like this node right here leaves? Then how is this node going to talk to that node? They're not within range anymore. It's a huge mess. How does this node deal with the fact that it's not connected to anyone else? So it's a hard problem. Lots of interesting research has been done on ad hoc networks. It is something that Wi-Fi supports, but honestly, it hasn't been well. It's there, it's part of the spec, but no one's really implemented it very well, such that it's super usable. Okay, so that's the introduction to wireless networks. Let's now cover the wireless links and network characteristics. So how are wireless links different than wired? That's really what I want to focus on. There's a couple of important differences. The first thing is this idea of signal strength and its relationship with path loss and how signal propagates. But that's not something we've been really concerned about in wired networks. In fact, we haven't talked about it at all. It is a problem in wired networks to some extent, but not nearly as much as it is to wireless. And the problem is that as you get farther away, or as there's more things between two nodes communicating, the signal strength weakens. The analogy would be, talking, right? If you're talking and you get really far away from someone, you might not be able to hear them anymore. As the sound travels to the air, it gets weaker and weaker. Same thing with wireless networks. There's propagation, path loss and propagation delays, and things just as it spreads out, it gets weaker. And so that's a problem we have to deal with. Now, because wireless is inherently broadcast, we have to now deal with other sources of interference, especially in these unlicensed spectrum where there's no rules. Anyone's allowed to transmit, which is a blessing and a curse. It's a blessing because that means Wi-Fi can transmit whenever it wants to, but it's also a curse because anyone else can also transmit whenever they want to. So we have to deal with weird interference. Microwave is a perfect example of this. If you're using 2.4 gigahertz and you run your microwave, if you're on the right channel of Wi-Fi, that microwave, and you have a cheap microwave, it actually might disrupt your communication because it's interfering with your Wi-Fi. There's some weird other ones, like motors can sometimes, when they run, radiate out interference at certain frequencies that can interfere with your wireless communication. So now we have to deal with other interference sources. And then we have multipath propagation. This is where your energy from your transmitter ripples out and bounces off obstacles, right? Bounces off walls. Depends on your frequencies that you're using. Some frequencies have more multipath issues than others. Typically, higher the frequency, the more multipath there is to a degree. So you can think of this as like rippling, right? Like in water, right? You drop something, the ripples go, and then they bounce off the edge of whatever container the water's in, and then reflect back. And so what can happen is a receiver might actually receive the same transmission multiple times because the line of sight, the fastest signal got there first, but the other signals that bounced off of things, they took longer to get there because they traveled further, so they might come at different times. What's really cool in modern versions of Wi-Fi, we actually use this to our advantage, and we can actually purposely delay our transmissions in specific ways so that the signals all come and add constructively together. It's called MIMO. So multipath is a problem, but we've actually turned this problem into a benefit, into a strength. So all these things make wireless links much more hard. You have to do all the stuff we've been talking about this whole semester, all the stuff that that networking provides, but now we also have all this stuff on top of it. So it's much more difficult, much more challenging in my opinion, and much more fun as a result. Okay, next we have different kind of characteristics we have to deal with our links. So there's this concept called signal to noise ratio. And it's an important thing to kind of get right. I know we typically like to talk about how strong is your signal, but really doesn't matter how strong your signal is. It only matters how strong it is relative to what the noise is, right? Because maybe your signal is really strong, but maybe the noise is just as strong or stronger. Then you've got a problem. Then you're not going to have a very good system. So let's think about sitting in a class. If no one's talking in the class right now, I can maybe whisper, and you might still be able to hear me because my signal is really weak, but the noise is really low. But let's say you're all talking, amongst yourselves, and I'm talking at a normal volume, a decent signal. You might not be able to hear me because of the noise is so high. So it's all about that ratio. So of course we want a higher signal to noise ratio. That allows us to see the signal, beyond the noise and be able to extract the signal. Say yes, I see this, and be able to decode it. So there's this trade-off of signal to noise ratio. It's measured in dB, decibels, and BER, bit error rate. There's this BER curves is what we call them. And so what we can do is say our system, whether let's say you're designing the next Wi-Fi, we want to be able to support a certain amount of bit error rate, something like this, and that's often drawn in this log scale. So notice how it's log scale. 10 to the negative 6. Let's say we just choose that. That's the rate, the amount of bit error we're willing to handle in our system. Okay, great, but how do you deal with different signal to noise ratios? Maybe you have a not great signal to noise ratio. What you can choose is different modulation schemes, ways of embedding the data in the analog signal. This is not a analog class, not a signal processing class. I would love to go more into detail about that, but just assume right now it's just different data rates. So the blue line is for low data rate, and so it can work decently well even if you don't have great signal to noise ratio. Whereas if you want to get the highest data rate, 8 times better, then you need a lot more signal to noise ratio. And maybe you have that. So good wireless protocols like Wi-Fi will dynamically shift between different modulation schemes, different uh, data rates based on the environment, maybe really close to the access point. And so you do have a really good signal to noise ratio. Then great, send a really fast data rate. But maybe you're far away, or maybe there's a lot of other interference sources. Then yeah, dynamically lower your data rate so that you still are able to achieve a good bit error rate. Okay. Yeah, I think I just described all this. Okay, another problem with wireless links is we have to deal with multiple senders. Uh, that's often handled through multiple access control. So, like time division, multiple access, frequency division. CSMA is what Wi Fi uses, carrier sensing multiple access. We listen before we transmit. So, let's think about the problem right here is uh, typically if I'm A, I would listen, say, okay, oh, no one's transmitting, and then you might send the data to B. But let's say you are C, you might be saying, okay, let me listen. Is anyone transmitting? And you wouldn't see A's transmission. You say, oh, okay, I guess no one's transmitting. You send to B. And what can happen is C and A could be transmitting at the same time to B. This is called a hidden terminal problem, also called the hidden node problem. Just depends on who you ask. Where two nodes, A and C, can both see B and B can see them, but they can't see each other. For some reason, it's always drawn with like a mountain between it. I don't know why. It doesn't have to literally be a mountain. It could be a brick wall. It could be just long distance. I mean, A could be over here and C could be right here. I guess that's what this diagram kind of shows. But at the end of the day, A has to be close enough to B where it can see B, but it can't see C. And then same thing with C. It can see B, but it can't see A. That's a problem. How do we deal with that? That's a hidden node or hidden terminal problem. A and C will send data at the same time potentially, or they'll interfere with each other at B, which is an important principle. Something that actually took me a really long time to realize. Interference only matters at the source. It doesn't matter at the transmitter. So A, if it's transmitting, doesn't have to worry about interference. C doesn't have to worry about interference if it's transmitting. It's only B who has to worry about interference when it's receiving the signal, because it's going to be receiving two signals at once, and then it can't, unscramble them. So how do we deal with this? It's another issue we have. There are solutions to this. Wi-Fi provides mechanisms to avoid this. Other protocols do other things. It just depends. Maybe for your network, it's not a problem. It just depends on what you're doing. But that just makes this a harder problem. Makes wireless links just a more challenging problem. Okay, so that's it. We'll talk about, like I said, we'll talk about Wi-Fi on Friday. And then on Monday, we'll talk about cellular networks. Hopefully you enjoyed this. I will see you all on Friday.